Hello, Sherry.
Hi, Tony. How are you?
I'm good. How are you?
Good, thanks. Looking smart there?
Thank you. Can you see me?
Yes.
I'm going to introduce you, Tony. So your CV is very big. What things must I emphasize?
Aubrey, are you talking to me?
Yes.
Sorry, you can't. You can write it, but
I have been given the pleasant but difficult task of introducing you.
Me?
Because your CV is very long. So I need to.
Mark, there are definitely two of the communication giants. Absolutely, recently, Alban Lynch, Professor Alban Lynch from University of Queensland, JK, founder of the JK, has passed away. So really, it was a big loss for the area. And just a few weeks before that, Professor Raj Rajamani from the University of Utah also passed away. So younger, of course, 70s compared to the 90s of Professor Alban Lynch. So definitely two big losses for our field here. So it puts us even in bigger shoes, correct? As communities to be able to fill this huge void that those visionaries left for us in the field. So I guess all of you already heard about, but it definitely saddens us as communities and as, of course, as people colleagues or these important fellows.
Yeah, I think it's important to acknowledge the fantastic work and foundation those people have put in. And the worldwide influence Alvin had was quite amazing. And Raj's work was best known for introducing DEM into mill modeling.
Absolutely.
Well, he did lots of other work, but he's best known for that.
Yeah. And I think it's interesting that the two people represent actually the two different approaches to comminution that some of us embrace today, because Alban left very down-to-earth modeling and plant-driven research, whereas Rajamani with CFD, first one applied CFD to cyclones, isn't it, and DEM, passing away over such a short period. That's something for us to think about and cherish their huge contributions. Absolutely.
Thank you very much, all. I think we are going to revert to today's seminar after those sad announcements. I think the comminution fraternity is very saddened by the passing of the two giants, and we hope we can learn from the things that they've done and move the science forward in this important field. We are now going to direct our attention to the presentation, our monthly seminar, which will be given today by Tony Anyimadu from Anglo-Gold Ashanti. Tony has been a great friend of ours for many years, and I have a very close relationship with Tony. I always tell people that the first thing I do when I meet Tony is always laugh, because when he greets you, immediately he conveys a joke or a light moment to make you at ease, and that is his trademark. Even when he was our sponsor from the Amira P9, he would make very good suggestions and in a very light way so that you can take them on board and move forward with your work. So Tony generally has a lot of experience in all the fields, particularly comminution, flotation, and extends beyond that to the business of mining. He is currently working as a vice president in Anglo-Gold Ashanti Technical. So he's been involved in reviewing many projects for Anglo-Gold Ashanti. Before that, he had worked in Anglo Platinum in the same capacity, where he oversaw many projects, and he has a lot of operational experience. So he's a well-rounded up metallurgist. He prefers me to call him a keen metallurgist who is enthusiastic about what he does. And it comes out in the way he interacts with us in this subject. So we look forward to the conversation that he will give with us today. He doesn't want me to call it a presentation, he calls it a conversation. So we look forward to that. Thank you, Tony.
Thank you for those kind words, Aubrey. Good afternoon, good day, good evening from the different parts of where you are watching. I'm actually quite happy to have this opportunity to have these conversations with you. And the context is really, I'm putting together, I guess 5 years to retirement, you start looking at legacy. So I've started putting together things. I think they were going to be about 6 volumes of collection of experiences. It may end up in a book or a thesis, or it doesn't matter how it ends up, but they would all be recorded. And so today's one conversation is really about some things I've picked up, the processing part of projects, and especially from the owner or the operator point of view. And I would really welcome a lot of discussions. So I hope that there will be time left for a little bit of discussions and conversations up and forth. Okay, so the context is this. I've always thought over the last 28 years that the whole process of doing mineral processing projects, whether they are big or small or mega, by mega I mean like say 60 million tons per annum, big I'm talking about say 20 above million tons per annum, and normal one is say up to 15 million tons per annum of gold projects. There are certain things that keep on repeating themselves. And the way I've sort of structured into it, and the way I think about it, is like a 3-pillar thing. The material variability, the ore variability in the occurrence of the ore and so on, whether it is disseminated, is difficult to get, or that's on the one side, which has taken millions of years to form. Then the circuit options, which keep on growing, thankfully, in the middle, and normally we work with the equipment manufacturers and so on. But linking all these is the proper understanding of the metallurgy and the process engineering, especially on the owner, or at least the owner's surrogate side, to pull these things together. And I've always thought that that means that there's always opportunity, rather than say a template, you get your quotation and you go ahead with it. I've always seen that loop, feedback back and forth, sometimes saves a lot of money, not just with capital, but also with life of mine and project OPEX. So that's a discussion we're going to have today. That I think in almost all the areas, there are opportunities to improve value. Okay, so that generally is what you're going to talk about. I'll start by setting why projects fail or how they fail metallurgically. And we need to establish the context right from the beginning that project management is a big thing. The management of that project itself is a technical area. That's what we are talking about. All the good ideas, time, decision, that is a big thing in the whole area with the PMBOK and the global benchmarks and so on. So we will talk about some of them, but it's not really, this talk is really about metallurgy as it applies to project management rather than the other way around. So let's get going. So why do metallurgical projects fail? A lot of time overruns, and then it either meets a good price, or doesn't take advantage of the good gold or platinum or whatever prices, and then it's no longer viable. The plant, but also the time value of the money that's in the project that we didn't take. The plant, but the technical area of why I think project fails, the first big one is that I think what the mining, practical mining can give, and what the metallurgy project process design plans in terms of capacity, flexibility, and many times you think that they go together, but it's not every time that they do go together. What goes together typically is that we have our drill core models, and then we make a project out of that. But in the middle, we should also really iterate with the mining in terms of where they can mine and where they can't mine, and when we expect to get what. And even if you have a blending or stockpile in the front, which some people do, some people don't, you still need to know what is going into those stockpiles. Why? Because of all variability and the throughput getting mismatched. So you typically have a place places where they run, and then for this they stop. So the metallurgy is too much capacity for what is available, and so on and so on. And you can't just say, oh no, don't worry, just stockpile enough to run. Well, stockpiling and blending is quite expensive. Anything that takes more than one handling is very expensive. But you could get quite a lot of value, but actually right at the project stage, matching not just what you have, where you have it, when do you think you can mine it, and if you can mine it, what are the things you do so that the metallurgy design and the mining talks together, so that you don't get the compromises through inappropriate circuit or insufficient circuit capacity. I will just give an example that if you already, there's a project that we moved from SABC to HPGR ball mill. Why? Because we realized that the material was quite variable, and the hardness especially. And we were going to create a lot of, on certain seasons, we were going to create just pebbles in the plant. Whilst the HPGR, for example, had a way of just crashing it down to size, pan-fully intended, and then the ball mill can deal with it. So those sort of things where you extract attributes right early so you can affect your process design. Many times it's missing. Why? Because many project owners just take the risk, what they deemed risk-free, and then they just get a quotation and then they proceed. So it becomes more like a predictable concept, pre-feasibility and so on and so on. And then they look around, benchmark a bit, and then they go ahead. But they lose a lot of the potential values that they would have got. Then other reasons why the project failed is unrealistic targets. And this doesn't come out because it is like people decide that they want to push it. Of course, when people are doing projects, they always want to put their best foot forward so that the project can be approved. But recovery overestimation happens a lot due to two main reasons. But one of the big main reasons is that the conditions at which recovery, at the initial stages, when the geologists get into the bushes and are able to access a sample, we do all series of tests, including diagnosis tests, and then some people just take the best results at the best conditions, but then people forget to take through those conditions and the corresponding OPEX and so on. And it sounds, oh no, it's an easy problem to avoid. No, it is not. Because once a value of a recovery gets into, people say that is the economic assumption, that's what you take to the market. But metallurgy is really, time anybody says great recovery, well, then you must just ask the questions, at what conditions? And then also the second part is the OPEX. People may not be willing to put 1 kilogram of cyanide in there. They'll probably put 500, but then it is the 1 kilogram that actually gave that 94% recovery. But that pieces of information get lost. So you get recovery, which is already established, and then you start getting, so what do people typically add here? And so on. And then, of course, as I said, the indemnity right from the beginning is that we don't pretend from the process engineering and metallurgy space that that's all that matters in project, not at all. There's a whole technical area of projects, which if you go to all those Anderson Consulting, all those, they have given reasons why projects fail, the technical part of the project failing, many, many things, price and so on. Teams not gelling, top heavy, waiting forever for corporate to give notes on decisions and so on and so on. So this is not some theory that you're talking about. This, of course, I won't mention where it is, but it's real numbers from one of our projects that you can see, you can read from this curve that two things, one very obvious things and one not so obvious thing. The one obvious thing is that the gold production was coming down and the revenue at some point, where is the gold produce came down and the revenue started coming down. But you can see the price influence there. But the first obvious thing from this graph is that the mining and the processing costs started going up as the material was going to get more and more difficult to recover, either to mine to reach it or to recover because it was either harder or more chemically complex. But the other things, so the reason why I cut this into two is that you could see it isn't just our normal engineering issues that made sure our cost was overtaking our revenue, but other things, G and A and so on. And this is where we group it into the other part of the project management. So what do you see from this graph? You see that that's a failed project. Well, eventually failed project. Why? Well, you're spending more than you can deliver. And it's not being, you can't even just blame the price. You can see that you are producing less gold and it is costing you more. So that's what I'm talking about. That this one is, sorry, is dramatic, but it's not always dramatic. Some are more insidious and it's inside. So if you don't use all your attributes you can use to refine at least the metallurgy parts of the project in tandem with the mining, you will be caught. And especially when the price starts going southwards. So what do we do typically in the project management? The global benchmarks, the Engineering Council of South Africa, there are different guidelines. And typically they are all quite similar, whether it's Latin America or Australia or where we operate or in Africa. Everybody sort of roughly understand class 0, class 1, class 2, starting from class 5 all the way to implementation. So what do you see here? That is the adapted one for Anglo Gold, which is concept phase, pre-feasibility, feasibility. I hope you can see my cursor, my mouse. Aubrey, can you see my mouse?
Yes.
Okay. And then to implementation, basically. So that's what it does going from left to right, as we all know. Then the plan, the kind of things we need at the different stages, we define them, and it is there. Definitions are there. Extent of the information you pick, it really depends on the metallurgical lead of these projects. And you have to get, of course, your plant capacity characterization, both for what you want and what you don't want, and design criteria and those things. The essence of this discussion is really to pick out things that are not so obvious rather than things that are too obvious. Okay. So we have something to guide us. Why? Well, the law has to make sure, especially if you're going to float your project on the stock exchange, then you have to follow certain procedures. But the first point in the abstract, which is how do you make a judicious balancing of not getting everything you need? Of course, you can't get everything you need. You only get everything you need characteristically when you start mining. But otherwise, you have to make an assumption, a calculated risk. How do you create that envelope of risk that I don't know everything about here, but I'm calculating that this project to go ahead at this point and so on. So here in AngloGold, as in many companies, we do stage gating. So the concept level requirement need to demonstrate one, technical and financial viability, just one, that the project can actually, it's possible to extract this all. Even though with some people who are very enthusiastic like myself, we actually just want to know that at least at the paperback exercise, where even at the concept level, how much gold will you get? And using whatever average of last 5 years gold, would you actually sell for profit, at least at that point? The financial requirement at that point is not that stringent, but it should at least be technically viable. But as I said, the right balancing of the information gathering and discarding possible routes need to be taken as early as possible. I'm not talking about in the concept phase, I'm talking about when the concept is finished. So because we have that in mind, and some of us influence that, we have actually broken the feasibility into two, that PFS, pre-feasibility into two. Pre-feasibility phase A, which is getting 3 or 4 potential routes, and then putting some financial numbers on it. And then as you are working to the end of pre-feasibility, your aim is to make sure that you only have one viable one. That's so, but you have to explain why you dropped the 2 that you dropped. So why is that? So that you don't carry a lot of these expensive things all the way through, which is very not so well managed projects tend to do. Okay, so the key decisions are taken, and the reasons why some are dropped, it's not because somebody likes the technology, but the mix of the material characteristics and attributes to the technology. Why did I push for this? Because many times you actually think that after 2, 3, 4 years into the project, you are still doing a suite of tests, almost like just to tick them off, to say, in case somebody asks, why didn't you use HPGR? You say, see, we did it. But it should be more scientific than that. And as I have already said, it is a balancing act. You get your analysis back to the miners, they do the optimization and so on and so on. But if you don't take care, you could spend 10 or 15 or 20 million on a project, whilst you could spend 5 million easily. Not in a, what do you call it, irresponsible manner, but in a manner which says, I'm targeting something, I don't get it, I take it out. Yeah. So that's what I just said. Okay, but just the last point on this is that the testing, a lot of those testing, means you have an idea in mind which route you want to take. It should happen, the test should happen prior to the study. And here I'm just splitting the study and the test. The study involves a lot of those things and the drawing and quotations and so on, while the testing is technical things that we all know about, the combination testing, hardness and so on, flotation, residence time, and those things we are all familiar with. So as far as the metallurgy part of the project is concerned, it is good to have some testing done and then use those testing to decide which study you take further. And importance of the metallurgical lead in selecting that correct suite of tests, that is worth their weight in gold, because then, as I said, you could end up doing, this is typically what people do without referring to your material type and so on and so on. You don't want to err on either side. So just to give an example of what I'm talking about, if say the full pre-feasibility study guidelines will cost typically 10 to 15, for a big project, I'm talking say 15 million or 20 million tons per annum, massive project, or a reasonably hard material that you want to extract gold out of. What the project itself may be these days about easily $1.2 billion. The steady part of it could easily be $20 million. Now, if you are a small operator or relatively small operator and you don't want to do the Rolls Royce, so what are the key things from that you do, or what are the kind of things that you have to do that you can get away with? That's if you just had, you could go and borrow say $1 million, say, what would you do with it? I would say from my experience, you have to do something that tells you material representativity and the extent of the variability. So those two are similar but not the same. So the test material representative of what you are testing costs a lot of money to get it at the beginning, but you have to. It will save you a lot of money later on. And then you also, by that, you know the extent of the variability. Density, I intentionally put it here because it sounds like it's obvious, but I'm sure most of you are communications, so you see how people underestimate the effect of density. They just look at the things like hardness and so on, but the different dense material do quite different things, both in the comminution and energy, but as well as in the hydrometallurgy portion. So because density is so nonchalant, people tend to go and take somebody's project and then sort of do their cost initially and say, no, we think this is enough mill size or whatever, or the plant size. And then you go and check and you say one is 2.75 and one is 3.5, and those are two worlds apart. The hardness at key size distributions, so hardness at the various key size, which give you, in terms of the project speak, options. As early, my philosophy is take it as early as you can. Not earlier. Take the gold out as early as you can, but not earlier. Because if you take it earlier, then the global optimum is suboptimal. But if you take it as early as you can, it hardly ever hurts you. So and then particle size distribution at different energy inputs. Of course, now we are linking to your kind of language. And again, the estimation of energy from the lab to the plant, I don't need to tell you, most of you guys, is sometimes not done quite, because the attributes in the material are not captured. So you either end up with an oversized combination circuit or undersized. Then now you are inching towards the cost side, which is the abrasive index, the wear rate that we expect, which is really going to live with us for the rest of the metallurgical project life. Cost liberation and recovery. So I've already spoken about sortability, grade engineering, heap leach, cost flotation. Why do agitated leach when you can do heap leach, for example? And then recovery and kinetics at different liberation and even all the way to diagnostic. Liberation to get you the design, diagnostic to explain to you why it didn't leach or float, and then if it can influence the design. Sorry. Then again, with the reagents, key rates of the consumption rates of key reagents, at what setting? And I keep on saying this, it sounds obvious, but these are the main reasons why people end up doing 200%, 300% of what they thought the stay in business capital was going to be. Because the project, every person who is doing a project typically will have optimistic tendencies and want to push the project up in a way that it will be signed. Why? Because you have to meet an IRR rate and so on and so on. Okay. Then if all your money was just 1 million, I would say after you've covered the technical areas, but as you have seen, not just the traditional technical areas, but what it could give you if you just went slightly slightly higher than what the prescription is in terms of seeing what opportunity you can get more than times. It will help you to make a very good decision. Then, of course, acid mine drainage and other hazardous tails and effluent and water balance. And again, that trips many projects because there's a lot of things with the water balance, inadvertent leaching of things that you don't want to leach and so on and so on. But water balance is a key thing now. Eventually, hopefully, now my sort of recommendation is that if you are starting the project, don't wait and commission it before you start thinking about digital twins, because as you are doing your models, even your laboratory, you start getting points, important points that will help you towards the way of the digital twins, which I don't need to describe to you. You need a model of it, but you need something beyond just a snapshot of that model. You need something that can replace the whole plant. And which better time to do those attributes than actually start collecting them when you are doing projects. So that would be and this typically will cost 20-30% of the money. You'll be surprised that but all the others, I'm not saying they are superfluous or they are not important, but they will come later on when you see the project is going ahead and so on. And some of them can even be deleted. But I'm not saying that don't follow the PMBOK or the EXA or the international standards. But I'm saying as a small operator or a medium, which are the things that are really, you can't do away with. These are some of the things you can do. Then we continue that discussion. In this whole presentation, we are balancing that triangle that I spoke about. So this is an iterative process. What are you seeing? You are watching a material representativity and its effect. So the yellow areas are the places where the samples were taken to be tested. And what typically happens is that you take these the geologists will draw these samples. You can see certain areas are not covered. Then, of course, the metallurgists will do the processing costs in the root of recovery cost and hardness and so on to predict the power. We get it back to the miners, they do their Whittle or other optimization. Then based on that, they leave some portions out or they leave some portions in. But it's an iterative process. Why? Because if you had taken samples from here, maybe even though the recovery may be low, it actually may be less costly to do it and so on and so on. So this is to give you an idea, and this is real data, which is this first input as a metallurgist that you can really affect a project's destiny from the CapEx to the OpEx to the life of mine, is to ensure that you understand that iterative nature of testing, taking it back. And in other words, I'm advocating for close collaboration with mining and geology. Geology and metallurgy are already going together because, of course, you need a sample from them. But the mining part, and many times is missing. And I'm advocating that by definition, your best project would be where you've actually done this iteration and explaining to the mining people the reason why you need to do it. So this is typically what happens. What you are seeing is the expectation of material through the plant, through the life of mine, which happens, of course, because this is where you are going to collect our money from. How many tons are going to go through the plant? So no problem there. But this is what doesn't happen. The not so obvious challenges moving from definition to execution is that the ounces expectations are typically almost always optimistically overestimated. Why? Because when you have something like this, I'm not saying the gradient of the curve is always like this. The head grade degradation through the years of operation sometimes happens, sometimes it's the opposite and so on, sometimes it's flat if you're lucky. But this is, again, every example I've used is my own example in real life. I won't tell you where the project is, but it's a head grade of copper. This is a copper gold thing. This is the expectation. The accountants or the project owners will, of course, account for the fact that the input into the project, the content of the gold or the copper itself is going down. So they'll be calculating a fixed percentage of it. That's fine. That's not the problem. The problem is that they should double account it. They should actually do the recovery model properly and incorporate it with the mining. So as you can see here, the recovery generally suffers as you expect, as the head grade goes down. So the head grade down here and recovery up here. So what am I saying? I'm saying that you should, in addition to the feed, the grade of the copper or the gold in the feed going down that you do your economics with, you should double penalize it by saying that when your low grades come, their recovery itself will also drop. It sounds obvious, yeah, but it's not so obvious in projects. When you chase it, you realize that if they did that assumption, some projects wouldn't go ahead at the time that they went ahead. Yeah. Okay, so that's the importance of that as actually to try and tease out some of the things that you do that will have big consequences, but they look like they are little when you're not aware of it and its implications. What about brownfields? And this one, so I said, how are new ore resources assessed so that the technical consequences are captured accurately while taking advantage of critical information already established in the processing of what? Why am I talking about this at all? Well, imagine if you have a plant that is already running and the miners have a new material coming in. Many times people are just blasé about it. They say, well, we know the plant, we know we've been running, it just is another material. But almost always the consumption, the OPEX, the recovery changes, and then we start chasing our tails because we don't give enough respect to that new material like the way we would give a respect to new projects. Why? Because we think we know the installed capacity, combination capacity, but to take our time and actually take that sum of material, sometimes all the way through pilot plant, even though you have a plan, so that you will know the influence of the mix. And this is one area that I'm highlighting for you, GCC, that sometimes whether it's mathematical averaging or lithology or whatever, that point really needs to be discussed in terms of what will be the so-called composite character, if there is ever such, or maybe you do both and compare and so on and so on. So I'll say combined recovery is very challenging, especially if you have things that punch above their weight, like Preb Robin and so on. You just need a little. So it's not, we all know it is not that proportional, but actually it could be even more unpredictable. So it's not a curve or graph. You really need to do so that you can put thresholds on it and then manage it quite nicely. Otherwise, you will always be chasing it. At least with the physics part of it, which is where a lot of you guys are working, the combined hardness and consequent throughput can be modeled with experience and so on. And even that, it's as we know, some of the hard, difficult materials will stay on, pebbles and load and all those. Even that needs to be done with care. But for recovery and for the downstream processing, you really need to treat it almost as if you treat material you don't know. All you know is your installed capacity. How the material will behave through that requires your respect and attention. Blending strategies are done, and the economics of that, as I said, anything beyond the one handling, you do two handle, double handling, many times it will erode the money or the profit you would have obtained, whatever that is bringing it, that ability to sort of push here, that sodio metallurgical aspect. If it results in 200 or 300 many times, it's gone. The profit is gone. So, for example, lithology testing. What is this one saying? I'm just pointing out one thing. So, for example, we gray wacke, schist, quartz, graphite, and so on, phyllite, whatever in whichever way. I mean, if you speak to the experienced geologists, inside here are also subdomains and so on. For example, so you will need to ensure that you take it through the process itself and see what their responses are, not forgetting scale up. Some of these materials scale up quite differently to others. Again, another interesting topic that people can look at. Why do some material represent itself in the actual installed capacity in such a different way from what it was predicted in the lab? Whilst others, you can almost plot one to one. Again, that would be an area that I would recommend some of your young ones to investigate. Then when you do that, this helps you at least in this case, I will not too far in terms of expectation, but look at what the quartz is saying. Now it's like a South African ore. The gravity recovery is 74. So then why put everything through when the gravity is 70, recovery is 74? At this current condition, it's not even tried to optimize it, for example. So you want quick gold, you can go for that. It gives you all the attributes that you could get, rather than saying, no, it's another material you have opened up, let's just push it through the plant. So trying to then conclude on that part, and then we go to the very final part, because I don't want to eat all the time. I would like us to have some good discussion. The key tools utilized, of course, it's a no-brainer. It's a JK Simmet, that's why we have been involved with Amira and things. And then here at the downstream end is the prediction accuracy, or at least predictability of what is going to happen. Then we model it, the material character. This is again another actual data from one of my work. That at least you have some things. Why is this just to look at, oh, you've got model parameters? No, not at all. This will actually affect the project capacity. The OPEX, how much carbon, how much cyanide you should take make sure you have reserved, and so on and so on and so on. How many elutions will you make? And therefore, literally the second part of the design is affected by the characteristics or expected characteristics of how it's going to be leached, how it's going to be absorbed, and then you can take it out. So I'm saying if you have this like P420, P9 models and so on, as a mineral processing project manager, you have actually no option but to get involved with it and get as close to the material character as possible so you can predict. So you can leave it. And in the old days, we learned from a lot of experience from the guys who used to do it. But now, in addition to that, you have to add a lot of proper analysis so that your prediction will be proper. So that even when you are benchmarking with other things, you will know, which is where the topic we are going to next. So so value add of a project, a project is typically like this. It's a material, we have oxide, diorite, schist in this case. They all have their proportions according to the geology and the mining people. They have their coarse parameters, hardness, and they have their fine grinding parameters and so on and so on. And then, as I said, do you average it? Do you test enough of it and so on? Do you test the first 4 years? And even after you've tested, did you use 75% passing P of the hardest, or do you use average, or do you design for the most safe, like 100% of the hardness and so on? All those are things you can advise as a project manager on if you understand what they mean and the consequences. And will you go for no chance of anything failing, or will you go for let's pay our bills and then after 5 years you switch to that one and so on? So there are strategies beyond the technical, but it always uses the technical input. So recovery and cost expectations as feedback to mining department. I've spoken about that, generating. Then this one, the fine tuning of throughput grind recovery window. Again, is a very, very important one. We typically just segment them and throughput and what is happy, and we do that, but we don't typically link it to the recovery loss that is going to happen. And it's not just the PAT, it's just the shape or the size of the distribution going to affect that whole recovery. So unfortunately, the recovery doesn't respect just the 1 point, which is the PAT, which is where many times we can, at least with the JK Simmet, which you guys, most of you guys have to develop, right? It's a distribution, all allows gets in there and helps it rather than just the power calculation of 1 point, which is some of the experience that we on the operation side have seen, that you can do an initial power calculation, but eventually you have to size that plant properly. And then the last point again, which is, of course, you can size and do your calculation, but the people who sell the equipment can only give you certain sizes, unless you have 4 or 5 years to wait for your particular one to be manufactured. Even that is not always possible. So this is a balancing act of how you do it. And this piece of work here is, again, probably the second most important piece of work that mineral processing project managers should understand the effect, the tools that we have now and how it links to the project life cycle. For example, that window I was talking about, this is real data on one of our projects. So fortunately or unfortunately, this is where you locate the PAT site of 75, 105, 150, 212, and they all have recovery implications. And of course, they have a kilowatt hour per ton implications. And what decision we made earlier on is that you can't use more than one SAG mill and you can't use more than 2 ball mills. Then so within that, what can you do? And so if you're going to chase recovery and lose tons as expected, or you're going to balance in the midway and so on. And actually, when you are balancing in midway, just be careful that you are not balancing based on easy material, because when you get to some of the hard material, there's no balancing on midway. If you don't get your 75 and you get 212, you're going to drop your recovery by so much, 10%. So when you are balancing, just make sure you have all the data information to balance with. Again, to illustrate the point that decision is not trivial. These things that you've got here, which are difficult to read for a reason, but I'm just guiding you through it, is output from 4 international companies with giving the same design data. All of them, you know them, so I'm not even putting. So the usual suspects, the usual people that do designs, they are all here, SABC. And you can see the differences in capacity that people are predicting from the different things. So I'm saying, as an owner of a project, you just have to work with it and then say what assumptions do. All these designs are correct technically. They are all tractable. They are all balanced and so on and so on. Certain key and not so key assumptions are quite different. And that's how you work through the process with them and say which ones you are going to take and which one you don't take. Benchmarking. Is it worth? Sometimes is it worth the trouble, or it's obviously you need to benchmark. You will benchmark whether you like it or not. Intuitively, you just look across your shoulder and see who is doing what and so on and so on. You benchmark. But sometimes is it worth it? I think the answer depends on how and when you apply it. So what is appropriate benchmarking? Are the benchmarks, so dollar per ton, dollar per ounce, you get these benchmarks everywhere from Deloitte, Intuition, and so on, and the mining magazines, and a gram per ton flotation, kilowatt hour per ton, ounce per ounce, dollar per, so in the geographical area and so on. Lixiviants, lime, gravity recoverable gold, which is one benchmark that is not really used much, which I'm proposing it should be used. Geological rock information and so on. Now, so the benchmarking should be done. The gap between the testing laboratory and actual performance makes it necessary to conduct some appropriate benchmarking. But the timing affects the importance of the benchmarking as early as possible, as soon as you start getting some information. But just be sure it's based on population size and you are comparing one unique project against an average guide. But again, everybody, if you allow metallurgists, everybody will tell you, no, my project is different. Sometimes they are right. 80% of the time, there's a lot of common attributes that you can actually take from other places. So for example, which of these recovery and cost benchmarks would apply to my project? It's 2 things. This is the recovery side for copper and gold, or I think I only put the copper here. And this is the cost side for that normalized for tons. Of course, there's economics of scale, which is obvious, but inside it is not as smooth, which tells you that, of course, the ores are different and so on and so on. Which of these final curve, where is my mouse? Can you see my mouse? I hope you can. So you want to influence both the final number as well as the proportions or distribution within it, for example. So at the very, very early stage, you can get a thumb sack. Here, I've used this quite a lot. Why? Because as soon as somebody tells me their project, they leached or they floated and they got, this is a flotation, by the way, and they got a 97%, which is possible. Leboa will give you 98% if you want. But in the circuit and after it's come out at a certain grade, sellable or not, as soon as somebody is on the extreme end, you can come back and say, okay, so are you telling me you'll be the 0.05 top percent? Then I say, that's fine. They all may be unique because we have 94 one year. Maybe you get 95. It's possible. But let's now look at where, so then I'll scrutinize it bit more in detail and say, why do you think you will do this 95 at this cost, which is the energy, the circuit, and then at this consumption rates? And then many times that's where the benchmark is useful. Of course, as the project advances into its phases, you are getting information of your own thing, and therefore you are basing your on scientific aspects and calculation. But the benchmark never stops. You pull back and then say, Tropicana, what are you using? Boddington, what are you using? And then you start asking more technical questions, not just overall cost, but what are you using? How many people are running this size of plant, and so on and so on. So it's an important one, but I think sometimes when the non-practitioners use benchmark and they want to cut it across to technical things, sometimes it's mismatched. And therefore, some otherwise good projects are discarded, whilst on the other hand, not so good projects are taken up. Because there are certain, when a recovery number hits people's head, if they don't understand it, it just takes what is the word? It takes a reality of its own. And as I said, the recovery in the metallurgy is really just a calculation. For example, you say, should the metrics be normalized for material type, throughput, hardness, liberation grind, where key minerals in it, copper easier than gold or whatever, head grade, key gang material, penalty elements, flow sheet. You can see where I'm going with this. Processing cost, key reagent consumption. So the question is, where do you stop benchmarking? So use it judiciously, but when you get to a point where somebody's benchmarking oxides and sulfides, you stop. For example, so that's benchmarking, and so far I've been highlighting material attributes and choices of technology and so on. But this one, it's too detailed, so we won't go into that. But I'm just saying that even after material characteristics, inside the technology itself, you can see this is a very complex plant. There's wet screen, rubber float, regrind mill, residue, separate pyrite, and the layout, and then in addition, you do like a filtration and so on. So inside itself, when they give you the quotation and the commensurate with the design, you have to drive around or fly around and just go see who is using it and how are they using it. And the reason is that you can basically save about 20 million on a 15 million tons per annum HPGR ball mill design. These are real numbers. Why? Well, how do you know you can save it and you not be being penny wise and pound foolish? You have to get into all the designs, the key areas that I've mentioned geographically through the plant. Take your suggestions or the new models, because you have to model it. So flotation, for example, is 5 times 500 cubic meter cells. You say, what about 7 times 300 cubic meter cells? Wow, counterintuitive. It's actually cheaper. Now let's model it back again, model it and see if this material character will be happy with that. Because it's not just the total residence time, as we all know. It's actually how that the residence time is distributed, for example. But you do all that and ensure that you've linked back. So what am I saying? I'm saying that even with the process engineering aspect of it, there's a lot of benchmarking or optimization work that metallurgists are supposed to do to make sure that they can save a lot of money there, rather than choose the most risk-free option. So these are real numbers that you do. So that's the major portion of what I'm talking about, that tuning the technology available, but even how you use it, you'll be surprised how much money you can save over there. And this is just CapEx, so you can imagine the life of mine. Again, I'm sorry, when you do this exercise, just make sure you've linked it to the other parts of the project. So water, if you're going to use more or less water, especially more water, just make sure it's linked in there so that the reticulation and everything is calculated. So you don't score here and then you lose overall all around. Yeah. I hope you guys are still there. Sherry, how am I doing for time?
We got a few minutes left, but we're running into discussion time.
Okay. So I'll rush through this. I'll try and get this published so that you can all read the details. Proper use of geometallurgical data, the proxy uses, as you all know, and especially I'm interested in hardness and recoverability. and the method of, but this is the big but, the big point I'm making. We should really scrutinize how that data was acquired, the grind residence time conditions. People do diagnostic leaching and apply it to expected recovery. And then we have to like spend the rest of the time chasing our tails to explain to the owners of the project why we are not getting that recovery. Example, you don't conduct all your tests at a fine or coarser crash or grind, and then extrapolate grind effect to recovery, which happens a lot. It's quite dangerous. I think things like liberation you can't extrapolate, and you need to test it at that point. And then there's so many options these days, but hindsight is 2020. But the consequence of bad design are a lot more than people sometimes see. I've already spoken to you about SABC being changed to crash liberation evidence. Even if you do lab and you force all the mass pull out, and it says no, there's no sensitivity of grind to recovery, don't believe it, because what happens in the plant is quite different from what happens in the lab, with the self aspiration and things cleaning and whatever, and recirculating and so on. So if there's a liberation grind, get there. Don't grind any finer, but get there, because the consequences are not always obvious in the laboratory. In GRG, use it. Residence time, use it. Modern technology, especially at the cost end of it, we now have quite a lot of options from blasting and so on and so on. We need to use it. For example, things that are not so obvious when you are doing your projects and you're following the procedures. When we this is public, so I can say the name of the place. So when we were trying to get Isomel across Anglo Platinum, we found that we were testing it at a certain nominal PAT, but when we set up the fines, which still were needed polishing by the Isomel, because that's where most of our platinum was actually inadvertently bypassing the cyclone, which is supposed to, because the cyclone is supposed, fine ones supposed to bypass cyclone. And then therefore they don't get attrition. But of course, just because the classification was proper doesn't mean that the metallurgy requirement will change. And so those are kind of things that are so difficult to test between the metallurgy science and the metallurgy engineering. But you need a midway to ensure that you've captured it. Yeah. So I will skip all this and I'll go to my concluding slide. So key lessons over the last 25 years. Matching of downstream capacity to comminution and throughput flexibility. Water reticulation and effect on process efficiency. Likely areas of bottleneck may actually be less regarded supporting structures like hoppers, chutes, drawings of angles and coatings. Those things will mess you up if it's not done properly. But I've also seen that high throughput covers a multitude of sins. So as long as you are pushing the throughput and even your efficiencies are dropped, but the gold is coming or the platinum is coming or the copper is coming, people can be happy, and that fool's paradise for 10 years. So last point, constructive skepticism regarding nice sounding claims. So for example, this is an actual thing from the study manager, which is the test work also indicates that preg-robbing nature of the ore is restricted to certain graphite zones, which can be identified and batch processed to minimize impact, number one. Number two, this allows a 50% reduction in the number of strips, saving an additional $0.86 per ton, which is a lot of money when you multiply by the tons. So at my sort of cynical old age, I will look at it and say, okay, that's fine. So the preg-robbing is there and it's only in that. But then all you have to do is just spend an afternoon with the mining guy and say, please, can you select those areas for me? It says you must be out of your mind. So you can't separate it, number one. Number two, the impact of that preg-robbing on the things and the residual effect on the water and the screens, and it doesn't just go because you passed it through. So these are some of the, I say, constructive skepticism. Skepticism, not just for the fun of it, but actually saying that, you are just looking at 1 + 1 is 2, but sometimes in the plant, 1 + 1 is 1,000. Thank you very much. I think I'll stop there so that we can have some good discussion.
Thank you very much, Tony, for that wonderful presentation. I'm getting a bit of feedback. Okay, it's cured now. Thank you for that wonderful presentation. I think we enjoyed ourselves and we almost forgot about time, because what you were highlighting in the presentations are the things that we need to know and hear collectively and see how these important decisions are made. Thank you for that. I'm going to open the floor for any questions for Tony. Let me just see I can see, is it Rollins?
Yes, thanks so much, Tony. I really appreciate that presentation. You can hear the wealth of experience you have in the different ways that you made it so practical. I guess I was just asking a question which is related to the graph that you showed with the project that highlighted how the costs and expenses of the plant varied over the years. And I guess the question which I'm asking is, in your view, how do you see environmental considerations as another way of adding to the uncertainty associated with the projects, particularly either on the technical side of energy considerations or on the other side of, say, social considerations? And then how do you see that balanced against maybe the opportunity that digital technologies of the future open up the door to reduce some of those costs in of different operations?
Oh, thank you, Lawrence. It's good to know you enjoyed it. Yeah, I have to be sort of quick about it, because the three topics you've introduced are like huge discussions. First, the energy, the environmental one, the energy is internal and it will impact on the cost, but it won't close the plant down unless the owners of the plant says, nah, it's costing us too much, we close it down. But I'll tell you which energy will close the environmental will close the plant down. Well, as soon as the streams, the smoke, the water, any of those things, that will close the plant down. And just as I could sort of indicate from the question, most times I agree with you that the environmentally benign solutions are actually costless. So, for example, when the water is the proper solution is found for that water before it's recirculated back, the technical effect on the flotation or the leaching is actually better. So it's better for the plant, the process, and it's also better for the environment. And now in general on that curves, there are some of those things you could have preempted, so that you would have seen that not so nice material is coming in 2 years or 3 years time. That you do at least allow the if nothing, at least the floor space for it, so you can put an extra tank when you reach there. So some of those things are self-imposed hardships. But again, when you have time, you can take a lot of those things over, and all those are very topical. And the last bit is the digital twin. Exactly. Once you've gathered all this information and you've made basically a digital twin or a model of it, but in a proper live dynamic way, of course, you can preempt some of these things that are difficult to see. It's a lot of things moving. The streams, like a place where you have diodes and so on, there are almost 900 streams of different interconnections. And they have pulp, they have solids in them. You want your money, so there's a main thing going on, but there are a lot of other things going on. And digital twins is a no-brainer. So I think when GCC took us to Aubrey, what's the name of that place in Zambia? Anyway, you started that discussion already, and I'm hoping that is really moving, because this is where we are going, both for environmental standard, meeting of that standard, as well as for profitability. Thanks, Lawrence.
Thank you very much for that, Tony. Any other further questions for Tony?
I have a question about that slide where you had the different stages from concept to pre-feasibility, feasibility, and so on. What about innovations? If I read that matrix, you have to present an innovation very early, because you lock down decisions, as you go there.
Sorry, I was talking to myself. Thanks, Magnus, for that. Very, very good discussion point. So you don't stop innovating. So the innovation will move through all the time, but it will be innovation within that you have picked, especially after the pre-feasibility studies. You're supposed to knock, if you have 3 potential routes in the metallurgist case, you're supposed to knock 1 out comprehensively or 2 out comprehensively before you move on to the next. But yes, to your question, the innovation doesn't stop at all, except that now that you have taken HPGR out, you can't go and bring back it in again. You now have to innovate around fine crashing, mine to, what do you call it? What is that? Final blasting having effect on those sort of things. What's the term, Malcolm? Blasting finance.
Dilution.
And what blasting finance, so you can gain in the sag and the ball and so on. So mixing that. So yes, Magnus, innovation will not stop. But if you have to make some hardcore decisions as you move through the plant, based on what material you are going to get and what require, so the innovation will happen. They will either give you a better operability, which eventually impacts on environment or on safety records, or they have to give you especially financial. Some of the HPGR, for example, you will always pay higher. It's almost 10-15% higher, but you get it back, especially if those matrices are aligned. If the material is hard and if the energy is expensive and all those things. So innovation, as opposed to research, the innovation will always continue. And then some of the research output to pour into the innovation bucket and we can still use it and it's a continuous process. But I'm advocating that don't continue using potential influence of innovation far way down when you are already going from feasibility to implementation about things that have nothing to do with your process that you have taken, for example.
Thank you. I saw a hand from David Seaman.
Thanks, and thanks, Tony. I hope you can hear me all right. I just wanted to ask, you mentioned variability quite a bit, and with comminution, I'm sure your norm is probably similar to ours of using a P75 when you're doing your design. In reality, you probably never really see that condition. What are your thoughts or approaches in dealing with the distribution of hardness? And it probably translates to almost all the metallurgical parameters there.
Yeah, fantastic question. Thanks, Dave. It's good to know you are on as well. So the decision on whether it's average or the hardest material, P75, is really the reason why we also do P75 is like you say, you really hedge in your bets. It's almost like saying, well, at least I wasn't too pessimistic or optimistic, that's really when it comes to it, because we haven't really, and that again would be a good thing to check whether when the plant is set up, especially the ore is not difficult, how many times of that P75 you see. But we haven't. We in Anglo definitely haven't, and that's something we could actually catalog and say the actual hardness. But then unless you have a digital twin, how are you going to get actual hardness that went through the plant, except by calculation, if you know what I mean? So that your input becomes the output and it defeats the purpose. But back to your question in terms of the real issue, the hardness changing, if it doesn't change in a block like the way it did in Sunrise Dam, many times you get away with it. So if the hardness doesn't change in a very marked way, it's a mix of things. And in fact, if you go to your plants and you see the log sheets and you see how much, even that 1 point, 75% passing 75 micro or P80 or P75, if you see that 1 point and the way that 1 point is fluctuating, you'll be surprised how it's still forgiving to us that we achieve our aim. So that's the one side. But the other side is what I was talking about now here is if you are going to encounter some really different P75 or P80 grind, you better know it, because you will know it, or the owners of the project will know it before you know it. So I hope I've answered you to some extent, but I think it's one of those topics that you can take an offside and discuss it. So P75 as part of, when we use it as a project, it's really, to be honest, we are hedging our bets. We are basically saying we are not too optimistic or pessimistic. That's why we use it, just to make sure we covered not our tracks, but basically that you put the project in the way where risk designing for the hardest material. I hope
Awesome.
that,
Thanks, Tony. Great presentation. Thank you.
Thank you, Tony. Is there, we can squeeze in a few last minute questions. It's rare to have Tony in this forum presenting, so we can stretch our luck a bit and get him more involved. Are there any other further questions? I can't see the hands here. While people are thinking about questions, I just wanted to pick up on one point that Tony mentioned. Yes, the GCC is putting together a project packaged on doing those dynamic simulations and how we can link this so that we can start seeing the perturbations in the system. So we are busy putting together, and we hope very soon or early in the next year, we can have we can send it to some sponsors and see who is interested to work with us on that. Malcolm?
Just switched off my... Unmute. Unmuted. Okay. Yeah, I was just wondering which of the 20 questions I should ask is the biggest challenge. You covered such a broad area, Tony. It's maybe just linking to what David is asking, the 75 marker and the variability. I have the feeling we lean back on it because we're building a plant that's fixed and you've got variable feed, but you can't actually do anything about it because the plant's fixed. So you just say it'll do. But if we built a plant that could respond, you wouldn't give the same answer. It wouldn't be a satisfactory answer, because now you would design your plants, you'd have a plant that can actually respond. So the grind size could change depending on what you need for recovery, the amount that would go to coarse recovery or to standard flotation, say, or leach. I think it's when we get to that point, we'll discard the single number. It's kind of a commentary, but I think that's what will drive that process, is when we design plants that are more robust instead of, it's a fixed plant for variable input. You're stuck, you're going to get a variable output, which you mentioned early on. So kind of a commentary and a question of what you think about that going forwards.
Yeah, I'm nodding my head here. It's the sort of recipe. In other words, if you like, the oil people do a bit of, they press on to different recipes based on material that is coming, the whole geomet concept. But I think once we have put on our design factors, and the equipment manufacturers have also put on that their design factors, most metallurgical plants are really way over designed. So yeah, unless you are sure that the sensitivity of grind to the other downstream effects all the way to filtration is not so important. If it is that important, then you would rather want to basically just have some of the things you are talking about, that ability to respond it and then readjust. So you all the way readjust your input so you don't mess up with that fine point. But if you don't do that fine, if you don't need that fine point, which was David's comment in most of our plants, then that's how you get away with that one number. So my comment to your commentary is that ability to demonstrate the need or the economic need of getting those, let's say maybe three different zones of liberation or grind. As soon as you can do the economic justification for that, people will pay money for that to be able to, and maybe the digital twin or the kind of graphs that I saw you, Malcolm, do at the end of the P9P, where that responsive plant that opts to take whatever cost, separation, density, those sort of things. Then that's where they all talk together. because ability to change your grind should be backed with what the actual effects and the added economic numbers that it gives you. Anyway, it's one of those things that you could still sort of discuss here.
Thank you very much, Tony, for those responses. I'm sure we can go on and on this, but maybe let me just give a chance for one last question, if there is a final question. If there is somebody burning to ask the very final question. Okay.
And by the way, just to everyone, Dave, Malcolm, everyone, the different sections that I've pushed here are really just a graph that represents a whole series of work. So anybody interested later can contact me now, dig deeper into some of those aspects. Yeah.
Thank you very much, Tony, and thank you for coming to give these wonderful presentations to us. I'll hand over to Marcelo to do the closing remarks. Oh, Marcelo said he was going to leave a little bit earlier, so he may not be here. But by way of closing remarks, thank you all for supporting these seminars. As the GCC, we would like to continue bringing more seminars to you. Sherry will post what the next seminar would be in due course. Unless Malcolm has a comment? Or... Okay, Malcolm.
Just to also say thank you to the people attending and very much to Tony for providing a industry presentation for us.
Thank you all, and we will see you in the next GCC seminar. And a very big thank you to Tony to take time out of your very busy schedule to come and interact with us. I think this is what the GCC is wanting to promote, so that the industry, the researchers can come together and share knowledge. Thank you for that.
Thank you. You are welcome. And thank you guys for spending a portion of your day with us. Thank you.
Cheers, everyone. Thanks for joining us.
Thank you.